I'm going to share my desktop. So this is a Cartesian system, and we know that there are x, y, z planes are there. So whenever we have a point over there, we say that this is a point, and similarly we can measure this point in 3 dimension, like x, some distances from the x-axis, some distances from the y-axis, and some distances from the z-axis. So we can measure the distance that are v1, v2, v3. So we can measure the distance of the this point from these 3 coordinates. So these are called v1, v2, v3. So the points coordinates are v1, v2, v3. Similarly, what happens if we put a vector over there from 0, 0 to that point? So that is called a vector from 0, 0 to that point, v1, v2, v3. So that is called a vector. So vectors are uniquely identified with the point in 3 dimension or 2 dimension, or in general n-dimensional Euclidean space. So in this course, only 2 and 3 dimensional vectors we will consider. We are not considering the 4 dimension, 5 dimension, more than 4 dimensions. We will discuss only 2 or 3 dimensions. So we see there is a vector v is equal to v1, v2, v3, and we can move this vector from anywhere in this plane. So no matter where in the space or in the plane you draw a vector, it always defines the point when the translated is parallel to the origin. So we can move either here, or we can move that vector from here to here. So, or anywhere in this plane, we can move this vector. There is no any change. So, so like this, we are drawing. It is showing that how the vector is going. So the next thing is the projection. So the projection means we will take a reflection, a projection, the projection of a vector onto the xy plane. Let's call it pxyv. Its image. What is the image of that vector? That's called the projection. So we will take in yellow color. You have shown. It's shown that it is a projection of the vector v. V is equal to v1, v2, v3. That's called the projection of that vector. So projection of xy or v is equal to what? This is the question. So it's equal to v1, v2, and the z coordinate will be 0, because of we always take a projection on the 2 dimension in 2 dimension places. We will take for example, if we have a 3D image, and we will take a Xerox of this image, 3D image, then the Xerox will become on the 2 dimension. So if we have a vector in 3 dimension, if we take a image, if we take a photocopy of this, then we can take a image in the 2 dimension only. So the image will be v1, v2, and the z coordinate, third coordinate, the third coordinate will be 0, because of image will always be in 2 dimension. So that's why the pxy will be is equal to v1, v2, and 0. That's called the projection. So this is in 2 dimension. So how we can measure it? From the Pythagoras theorem, we can measure it. So Pythagoras theorem, like v1 is square plus v2 is square, we can measure. So now the next is what about the length of the vector? So apply the Pythagoras theorem again and obtain it. So when we obtain the Pythagoras theorem, we can obtain that is this v square is equal to hypotenuse square is equal to perpendicular square plus base square. From that we can obtain a v1 square plus v2 square plus v3 square. So now similarly, how we can measure the magnitude of this vector? So the magnitude of this vector can be obtained by taking, as I told you in previous lecture, just taking the under root and taking the squares. That's you can take the magnitude of this vector. So if suppose a vector is given -2, 3, 6, and you have to find the magnitude of this vector. Magnitude means what is the length of the vector. So if magnitude, find the magnitude, so we will take the under root and take the square of each element. So we can take the under root and take a square. So that will be equal to 2 to the 4, 3 is a 9, 6 is a 36. That will be equal to 49. So 7 is a 49. So we get 7 will be the magnitude of this vector. So a very special vector pointing from the origin to the origin is called a zero vector. So zero vector means it starts at 0 and ends with the 0. That's called the zero vector, and it is denoted by 0. So what are the coordinates of the zero vector? So the coordinates of the zero vector in 2 dimensions you can write 0, 0. In 3 dimensions you can write 0, 0, 0. In 4 and 5, 6 dimensions you can write so many zeros are there. So adding of the vectors, it is given here when you have 2 vectors and you are going to add these 2 vectors. You can add these things, and if you multiply any scalar with the vector, then the whole vector you have to multiply. Like this, if we have a v vector, we multiply with the 2. So every element we have to multiply with this. So like this, we can multiply. So if we have a vector v is equal to v1, v2, v3, then what is the negation of the vector? So if we multiply -1 with that vector, that will be is equal to -1 into v1, -1 into v2, and -1 into v3. We can write like this. Similarly, if we are going to subtract the 2 vectors, so in mathematics, as I shown you, but in figure you can see this. You can subtract this. If you are going to subtract the 2 vectors, then you have to draw this type of image. Any vector on the blue line passing through the origin is of the form alpha into v. So for example, this is a line. Any vector you can draw on this line, this will be written as alpha into v. So alpha into vector v. What should I do if I wanted to write an equation of a line that does not pass through the origin? So we will, for example, this is a line and it is not passing through the origin. It is something apart. So we have this distance from the origin. So for example, this is a vector v. So we will take another vector and just take a triangle, and from the Pythagoras theorem we can find it. We can find it like this. So these are something. So unit vector in the direction of A. So for example, if you have vector A and you have to find the unit vector, then you have to split it in each component. You can write A upon mod A, A2 upon mod A, and A3 upon mod A. In this way, you have to write like this. What are the coordinates of the scale unit blue vectors? So what are the coordinates? The coordinates, it's a unit vector, so its coordinate will be v1 square plus v2 square plus v3 square. So there are some laws that we use in a vector space that you have to, all of you are aware about this. The first one is called the associativity of addition. So associativity means v1, if we have three vectors v1, v2 plus v3, then we can, it will be equal to, v1 plus v2 and v3. Similarly, commutativity for addition, and v1 plus v2 is equal to v2 plus v1. These laws are helpful in the vector space. So I will tell you, we will discuss the vector space later on, but before, you will discuss these properties. So next property is identity of element in the addition. So there exists an element 0 belongs to V. It's called a zero vector such that V plus 0 will be equal to V for all V belongs to V. This is called the existence of identity. Similarly, next property is existence of inverse element. So there is an element V belongs to V. There exists an element minus V belongs to V. So that is called the additive inverse of V, so that V plus V. The next property is the distributive law. So distributivity for the scalar multiplication with respect to vector. So if we multiply any scalar s with the vector v plus v1, then it will be equal to, so sv1 plus sv2. That's called the left-hand distributive law. So similarly, distributivity of scalars multiplication with respect to the field addition. So if we have two scalars and one vectors, then we can write n1v, n2v. Similarly, respect the scalar multiplication over the field multiplication. So if we have two scalars n1, n2, and there is a scalar and there is a vector, then we can write n1 into n2, and we can write vector. Similarly, identity element of a scalar multiplication. So for a scalar multiplication, we have a identity is 1. So in case of addition, we have an identity element is 0. Note that in case of addition, our identity element is 0. In case of multiplication, our identity element is 1. So these are the differences. So these properties we will use in the vector space. So in 3-dimension, we are most of the time we assume the three vectors, that is I, J, and K. So these three, these are called the unit vector I, J, and K, and these are standard unit vector. They are called. So I in the direction of X, J in the direction of Y, Z in the direction of K. So this is called I is equal to 1, 0, 0. These are called the standard basis, standard vector. And J we will count 0, 1, 0, and K we will take 0, 0, 1. So these are called the standard unit vectors. Are there unit vectors? So remember this, because of these results we will use later on. So rotation in 2 dimensions. So it is given here. So you will see this. There is an example. So now there are two types of products as we discussed in previous lectures. One is called the dot product. Another one is called the scalar product. So this is cross product and dot product. So this is called the scalar product, that is, or you can say dot product. So the meaning of dot product means A dot B will be equal to mod A mod B cos theta, or A dot B upon mod A is called the component of B in the direction of A. The figure of A dot B will be like this. It is given here. So this is the formula of A dot B. So notice that this definition of a scalar product of vectors is coordinate independent. So what happens if we were to introduce the coordinates? So for example, if we have a coordinates are there, and there is a v1, v2, and there is x is equal to x1 and 0. So mod x is equal to x1, and v is equal to cos theta, and next this is a 90-degree angle. So that's cos theta will be v1. We know that So it is v. So that's x into v will be equal to x into v cos theta. That is x into v into dot cos theta, and that's x into v x dot v1 plus 0 dot v2. So, and notice that any pair of vectors is obtained via rotation by some angle alpha of a pair in the special case discussed on the various slides. So these are the examples of the dot products that we discussed in week number 5. Now next we will discuss the cross product. As we discussed, there are two types of product, dot product and the cross product. So we will discuss the next type of product, that is called the cross product. So next type of product, that is called the cross product, and it is written as a cross b will be is equal to mod a mod b sine theta. Sine theta means is the angle, and its graph is like this: a, b, and n is the unit vector, or a cross b. So a cross b will be is equal to mod a mod b sine theta into unit vector n. N is always be in up direction, or it is in thumb rule, you can say. So it is given here direction is the direction of n, where n is the unit vector of a and b, such that a, b, and n form a right-handed set. And if you come, n is always be on the top. If you turn your your fingers, and wherever the direction of your thumb, that is called the unit vector. The magnitude of the vector product gives an area of the parallelogram spanned by A and B. Next is, if A and B have the same direction, then sine theta will be equal to 0, and A cross B is equal to 0, the zero vector. So these are the definition of cross product. So cross product means whenever we have I cross I. So I cross I means the same thing, and we know sine 0, the value of sine 0 is 0. So I cross I sine 0, so it will be is equal to sine 0 0, so it will be is equal to 0. Similarly, j cross j sine 0 will be is equal to 0, and k cross k sine 0 will be is equal to 0. So we can say whenever we write I cross I, j cross j, k cross k, its value will be 0. And whenever I write I cross j, we will take a next one, that is the k. J cross k will be equal to I, and k cross I will be equal to j. So what happens if we take a negative of any j? What happens? J cross I, that will be equal to minus k. Similarly, k cross j, that will be equal to minus I, and I cross k, that will be equal to minus j. So this is the way to write a cross product. So in cross product we have a mod b sine theta. In dot product we have mod b cos theta. So this is the only difference between a dot product and cross product. So these are several examples are there. There are the line spaces, so you will read it. There is there is no need for it. You can read it. So next topic is length of the product of length and dot product of the vector space. So how we can find the length of a vector? So the length of a vector we can find from the norm. This is the symbol is called the norm of v. So norm of v will be is equal to under root v1 square plus v2 square plus vn square. So the length means you have to find the norm. Whenever norm is written, you understand that they are asking for the length. So it is written here, the length of a vector is also called the norm. So the properties of length is always be positive. It is never be negative. And the second property is if the length is equal to 1, it means V is called a unit vector. If length is equal to 0, if and only if V is equal to 0. And next one is C into V is equal to C norm of V. So, for example, a question is given, if V is equal to some vector is given and you have to find the norm of this vector. So what you did, you will take a under root and take the whole square, all these things, you will get a norm of this. So you under root 0 square minus 2 square plus 1 square plus 4 square minus 2 square, and adding all them. So you will get under root 25, that is equal to 25, and 5 5 is 25, that is equal to 5. Similarly, what is in Rn is given by, so what is the norm of this? A vector is given. So what we did, we will take a norm. Norm is just under root and square every element. We can find the norm of this vector. V is a unit vector. So it is, you can say that V is a unit vector after finding the norm. So now again, as I told you, the standard unit vectors in the figure, as I show you, the standard the E1, E2, En are called a standard unit vector. Yani, if it is equal to 1, 0, 0, 1, then it means it is a standard unit vector. And in 2 dimension we can written here, in 3 dimension we can written here. Two non-zero vectors are parallel. U is equal to CV. If these two vectors are parallel, then we can write U is equal to CV. C is the multiplication on the same direction. A vector is in the same direction with several constants are there. If C is greater than 0, U and V are the same direction. If C is less than 0, that is negative, then these two vectors are in opposite direction. So this is a very simple thing. So this is the theorem. It says that if a V is a non-zero vector, then the vector U is equal to V upon norm V. So it is a theorem. You can find it. So the vector V upon norm V is called the unit vector. So we can find the unit vector from this theorem. So the question says that find the unit vector in the direction of V and verify that this vector has length 1. So first of all, we will find the formula of the unit vector will be V upon norm V. So first of all, we find the norm V. Norm V will be equal to 14. And after that, we will put the vector V upon norm V. So V upon norm V is equal to 3 minus 1, 2 upon under root 14. So we can put it and we get this. This is a norm of a vector. And if we take under root and square, so we will get 1. It means it is a unit vector. So the distance between two vectors U and V. So as you know that distance can never be 0. And if the distance is 0, if and only if the two vectors are both are equal. And distance of UV is equal to, we can say that distance of VU, both are the same thing. There is no any change. So find the distance between two vectors. The two vectors is given U and V. They say that find the distance. So we can find the distance by subtracting these two vectors. And U minus V, when we subtract these two vectors, we will get 0 minus 2, 2 minus 0, and this every element to every element we get a 3. Similarly, we can see the dot product and cross product. Again, they are giving you some example. It is given a vector U and vector V, and they have to ask the question, find the dot product. So we will multiply first element to first element, second to second, third to third, and so on. So there are several properties of the dot product, commutative law, associative law, existence of, and several more. So now let's see find the dot products of this. So can you guess what are the dot product of u dot v? So I'm giving you 1 minute. You just guess what are the dot product of u dot v. So we will find u dot v. First of all, we will find u dot v. So when we multiply u dot v, that will be is equal to 2 multiplied by 5, and minus 2 multiplied by 8, that will be is equal to minus 6. Similarly, if you multiply, next question is u dot v dot w. So it means we already find out in, say, question B, we already find out u dot v will be equal to minus 6, and we have to multiply w. So we can write that minus 6 into w, that will be is equal to w will be minus 4 into 3. So we will multiply 6 4s are 24 and 6 3s are 18. That's why my 24 and minus 18. Now, so question number C is u dot 2v. So first of all, we multiply v into 2. So 5 2s are 10 and 8 2s are 24. 8 2s are 16. So we multiply this, and after that we will multiply u. So let's see what happened. So we multiply 2 into, or this is another method. They use the another method. They will take 2 outside and just multiply u dot v. It's also good. From the from the equation 1, we can find that u dot v will be equal to minus 6. So we just multiply 6 to the 12. It's also good. Either you can do from that method, or from any method you can use. So from the D part, it says that norm of w square. So that we can write w into w. So w into w we can write 4 into 4 and 3 into 3. And that will be equal to 25. And the last one is u dot v minus 2w. So in this again we can write just component to component we will write, and we see this, we will get a 22. There is a dot product. Hopefully understand how we can operate like these things. So next question is, using the properties of the dot product given u dot u is equal to this something u dot v dot v, and find u plus 2v dot 3u plus v. So some rules are given, and you have to find the value of this combined statement. So we can write u plus 2v dot this. We can written just elaborate it, just expand this. So when we expand it, we can write u dot this and plus 2v dot something. So now further we will open the bracket. So we will find 3 is the outside, then u dot u will be, and the next one is u dot v. So we can write like this. We can write 3 into u. So 3 will be outside. So we can write in u dot u, 3 into u dot u and u dot v, and in this way. Now put all the values from the question. It is given here. When you put all the values in the question, you will find you will put u dot u is equal to 39. Just put all these values here. You will get a 254. So this is the method. In this way, we can find the solution. So these are the cos. The angle between two vectors will be cos theta is equal to u dot v upon norm u norm v. Theta will be equal to 0 to pi. So when theta will be pi, the cos theta, we know that cos theta will be -1. When theta will be is equal to pi to 90 degree, the cos theta will be less than 0. And these values you have to know. Now, next thing, finding the angle between two vectors. The vectors are given u and v. It says that find the angle between these two vectors. So norm u will be this. We know that the angle between two vectors will be u dot v is equal to norm u norm v upon this. So we can write like this: theta is equal to this. Orthogonality of the two vectors u and v are orthogonal if and only if u dot v is equal to 0. So we can write the vector 0 is called the orthogonal to every vectors. So finding the orthogonal vectors, there are two vectors are given, u and v. So u dot v will be is equal to something, and it is given v is equal to minus t1 upon 2, v2 is equal to t. So v is equal to minus t upon 2, comma t. T belongs to real number any. So triangular inequality, this is the theorem. You can see this theorem and vectors in Rn. So these things we will discuss, these slides we will discuss in our face-to-face class. So hopefully you understand these all things. If we have two vectors, how we can put them equal, how we can put them to equal. That's if we have vector u and v. So u is equal to v, or if we have two vectors u and v, if we are going to add, then we will add the corresponding elements u1 to v1, u2 to v2, u3 to v3. Similarly, if we multiply any vector with the constant, then we have to multiply every element of that vector. So these things we discussed already. So here there are the two questions are given. They say that if we have three vectors u, v, and w, vectors solving them, and we have to solve these vectors, find the value of x. So when you will find the value of x, you have to multiply the vector u, v, and w. Just put the values of u, v, and w. So when you put the values of these things, you will get x is equal to 2u minus v plus 3w. That is, and just put the value of u. The value of u will be 2 minus 150. So when you put that will be 2 to the 4, 2 minus 1 is 2, and 2 5 is 10, and 2 0 is 0. So you will put the value of u here. Similarly, you will put the value of v, that is 4 3 1 minus 1, and similarly value of the 3w. So multiply w with the 3, that will be equal to 6 3 is 18. In this way, you can find the values. Next one is b part. In the same way, you can find the b part, that is 3x plus w will be equal to 2u minus v plus x. That is equal to like this. In this way, we can find. So just take the x on the left side, and w will be on the right side. You can find the value of x, y, that will be equal to 2150. You can find the value of in this way. So properties of additive identity, linear combination. So this is a linear combination that I told you. The linear combination can be written as x is equal to c1 v1, c2 v2, and cn vn. So this is called the linear combination. So we are using this linear combination to prove whether it's to prove the linear dependent and independent. So whenever I write a vector in this form, that is C1 V1 C2 V2 Cn Vn, it means that it is called a linear combination. So after a few slides, I will show you how we can represent a linearly dependent and linearly independent with the help of linear combination. So first of all, we will discuss some example of the linear combination. It says that we have three vectors u, v, and w. U, v, and w. There are three vectors, and we have to write in the form of the linear combination. And it says that find the value of a, b, c. So first of all, we can write these three vectors in the form of in this way, that is 0a minus 1b minus 3c is equal to this, that is equal to minus 1 here, minus 1 here. Similarly, the next is 1a here, 1a, 1b, and 1, 3 will be equal to minus 2. So we will write the three equations, three unknown. So we can solve these three equations and three unknown by Gauss elimination or Gauss-Jordan method. We will get the result. So these things we discussed earlier. So now the next topic is vector space. So in vector space, the definition is let V be a set on which two operations, vector addition and scalar multiplication, are defined if the following axioms are satisfied for every u, v, and w in V and every scalar real number C and D, then V is called a vector space. Meaning is that there are 10 properties are there. If all the 10 properties are whole, then we say that it is a vector space. If any one of the properties is not whole, then we say that it is not a vector space. So the 5 properties belong to the addition, that is a addition for u plus v belongs to V. The second property is commutative law. Third property is associative law. Fourth property is existence of identity, and the fourth property is existence of inverse. Similarly, we have 5 properties for the multiplication. These are the 5 properties that are called, and this is the scalar multiplication, that is the distributive law, Lefton distributive law. And this is again, if we have 2 scalars, C plus D, and multiply by with vector, and there is again these 10 properties we have to follow. If any one property are not whole, then this is not called a vector space. So you have to remember all these 10 properties. And the vector space is written as V plus dot. And this is the symbol. In this way, we can represent a vector space. So 0 is a vector space, and there are some other definition. So the question is whether a set of all integer is not a vector space. You have to show. So we will show all the 10 points. It is hold the commutative law, associative law, existence of identity, existence of inverse. When we reach the point number 6, so let us we take any integers. It is called any integer belongs to vector space. So let us we take an integer 1. 1 belongs to vector space. And let us take any constants. So any constant that is 1 by 2, any belongs to real number. So when we multiply constant with the vector 1 by 2 into 1, so we have to give 1 by 2, but it is not belongs to vector space. So our point number 6 is not satisfied. So it means that it is not set of all integers is not a vector space. Similarly, the second example is the set of all second degree polynomial is not a vector space. So for example, we take a one polynomial that px is equal to x square. We take another polynomial qx is equal to minus x square plus x plus 1. So when we we have to check all the 10 properties. So when we are going to check, so the property number 1 is not satisfied. That is, when you are going to add these two, they are not belongs to the vector space. Because of x square to minus x square is cancelled out, we will get x plus 1. But x plus 1 is not a second degree. It has only a 1 degree. So that we can say that it is not a vector space. Next one is subspace. Subspace is a part of the vector space. Is a part of the vector space. So W is a subspace of V. So to check whether it is a subspace or not, we have to check it on the only two properties, that is U plus V is in W, and the second property is if U is in W and C is in a scalar, then CU is in W and CW is in belongs to the vector subspace. So if these two properties are whole, then we say that it is a subspace. So remember that a subspace, a non-empty subset of a vector space V, then W is a subspace of V if and only if the following conditions hold. So these two properties are whole, then we say that it is a subspace. So there are several examples. So the example first, it says that let W be a singular matrix. The singular matrix means whenever their determinant will be is equal to 0, so that matrix are called the singular matrix. So for example, we have a singular matrix A. A is a singular matrix. If you multiply 1 into 0 is 0 and 0 into 0 is 0. Determinant will be is equal to 0. So it is a singular matrix. Again, let us check B. B is a singular matrix. Just multiply 0 into 1 minus 0 into 0. That's 0. So it is again a singular matrix. So we have two matrices, A and B are singular. So, and both are belongs to the subspaces. So when let us we check whether it is a subspace or not. So we have to check the two properties. That's the existence of any additive identity. When we are going to add these two, that will belong to the subspace. So let's we check. So when we add the two matrices A and B, and we will get 1 0 0 1. So let us check it is a singular or not. So when we check 1 into 1, that is 1, and minus 0 into 0, that is 0. So 1 minus 0 will be equal to 1. So it is 1. It is not equal to 0. It means it is not a singular matrix, and it is not belongs to the subspace. So it means that it is not belongs to a subspace. So that's we want to show that. So similarly, some more example. M2 W2 is not a subspace. Similarly, there are some more examples you will see it at your home because of I discussed this on my face-to-face class. You can see there. So the next thing is linearly dependent and independent. So there are two things dependent. So it says that if we have a vector S is equal to V1, V2, Vk, the set of vectors in a vector space V, and it is a linear combination C1, V2, and C2, V2 is equal to 0. So if all the C's are 0, then we say that it is linearly independent. If any one C is not 0, then we say that it is a linearly dependent. So for example, let's take an example. So we have a set is given S is equal to something. So we have to check whether it is linearly independent or linearly dependent. So what we did first we will write in the form of linear combination. So we will write C1 V1, C2 V2, C3 V3. So when we write C1, C2, C3 V3, and just put the vectors in place of V1, So we write C1 V1 and put the three equations, that is C1 V1, C2 V2. So with V3 and C3 V3, we write like this. Yani 1 into C1 and 0 into C2 and minus 2 into C3. So we write in this form, we can get a matrix. So similarly, uh, in this way, we can write the matrix, and we are getting a matrix in this form that will be is equal to 1 0 0 and 0 0 0. So our whole row will be 0. So that is why we say that this is a matrix. Yani, what is the value? Anyone tell what is the value of this? So what is the call of this? Tell me, what is the solution of this? So we have a value x is equal to 0, y is equal to 0, z is equal to 0. So we are getting these values. Similarly, C1 is equal to C2 is equal to C3 is equal to 0, only the trivial solution. So tell me whether it is a linearly dependent or independent. So we say that it is linearly independent because of all the C's are 0. Similarly, the second question, we can see this like this. In the same way we can prove that, and here we have the value of C1 is equal to 2, C2 is equal to minus 1, C3 is equal to 3. So we say that it is linearly dependent. So it's up to n. We can so your lecture is n, and yes. So if you have any question, then you can ask me. Okay, it's all right. So if you don't have any question, then it's all right. Good. Good ask. I will check whether you will try to solve the assignment with yourself and try to submit on time. Otherwise, I will give you the solution on the next day. And after that, if you have any problem after the solution, then you can discuss me. Okay, I will be there in the university. You can come at my office. After, if you don't understand the solution, then you can come to my office. I will tell you the exact uh, how we can solve it. Okay. So okay. Good night and have a nice day.
Recording stopped.
The midterm, as I told you, the midterm is 60% from the assignment and 40% from the outside. So mainly you will focus on the assignment. Okay.